Now I am going to explain you about a basic operation of an N-channel JFET. So here I am considering one N-type silicon semiconductor bar, and I am injecting two P-type materials across a gate terminal, so it is going to form a two PN junctions, and the ohmic contacts are drain and source. So here the majority charge carriers are electrons, so the majority charge carriers always enter into a bar through a source terminal and always will leave the bar through a drain terminal. So here, to know the basic operation of this N-channel JFET, here I am considering the two voltages. One is gate to source voltage, here input terminal, and the drain to source voltage, output terminal. So depending upon these two voltages, we are explaining the operation of this N-channel JFET. So in this one, the first condition is under no bias condition. So when we are not applying any voltage, okay, so the device will be in a ideal condition. So there is no output current or drain current. So the device will be in a cutoff region. Similarly, when this case 2, so when the input voltage is negative, so here I am making the input voltage as one time negative value, once 0 value. Similarly, drain to source voltage as 0 value and greater than 0 value. So here I am taking the two voltages. One is lesser value in one condition and the other one is an incremented value. Like if VGS is negative, then VDS is 0. This is one condition. And the another case, I am increasing this VGS as 0 and increasing the drain to source voltage as positive value. So here I am taking the second case when VGS is negative value and the drain to source voltage is 0. So here this is the N-channel JFET. Okay, so again here I am taking the gate to source voltage as more negative value and less negative value. Okay, so here when the gate to source voltage is more negative value, so the negative terminal of the battery is connected to the P side and the positive terminal is connected to the negative side, source side. Okay, similarly here VDS is 0 means here simply will making the shorting the this drain and source terminal, so which is connected to ground. Okay, so here coming to its operation, so here the junction gets reverse bias conditions. The width of the depletion region gets increases. As the width of the depletion region gets increases, the channel width may becomes very narrow. Okay, as here the drain to source is grounded here, so the negative charge particles, nothing but majority charge carriers, electrons will flow through the source to a drain through this narrow channel. So the conventional current is generated that is very small compared to the another cases. Similarly, here I am increasing the VGS value to a another value, nothing but minus 1 volt. So here it is minus 4 volt, here it is minus 1 volt. Whenever we are increasing the gate to source voltage to some more positive value, like minus 4 to minus 1 means we are increasing the gate to source voltage. So in this condition, this negative terminal, positive terminal, the junction gets reverse bias, but here the width of the depletion region gets smaller compared to the previous case. So therefore the channel width gets wider compared to the previous cases, and here the more number of majority charge carriers will flow through the source to a drain terminal, so the more number of current is generated. So by this way, if we are increasing the VGS value from negative to positive, so the more current is generated. So by this way, the drain current after a certain value, it will reaches to a saturated value. Okay, so now this is a third condition. So this is the third condition. In the third condition, when VGS is, so here it is minus 4, it is minus 1, like, and the next value is VGS is equal to 0. Now we are making the drain to source voltage greater than 0. Okay, now we'll see what will happen if we are going to increase this drain to source voltage more positive value. So in this case, again here it is 0 means it is connected to a ground terminal, gate to source is connected to a ground terminal, so negative terminal, positive terminal, the width of the depletion region gets increases. Again here we are increasing the drain to source voltage more positive. Okay, so in this condition the FET acts like a voltage variable resistor here, because whatever the voltage you are applying, so because of this channel it is going to oppose the increase in a drain current, because as the width of the depletion region gets increases, okay, it is going to oppose the more drain current, and at a certain point value these both depletion regions met each other, so that certain value is called as pinch off voltage. Okay, so this is the VI characteristics. Okay, so therefore when VDS is equal to 0, the drain current is 0, as we are increasing the drain to source voltage to a positive value at a certain point value. Okay, so that voltage is, the current reaches to a maximum value, so that certain point value is called as pinch off voltage. Okay, so this is called as a cutoff region, this is called as a ohmic region, this is called as saturation region. Again, if we keep on increasing this value, the device enters into a breakdown region. Thank you.